Hi, welcome back. I'm Professor Ridge, and today's lesson's section 1.7 on scientific notation. So starting off with the definition of scientific notation. Okay, scientific notation for a number is an expression of the form n times 10 to the m, where n is in decimal notation. And n is between 1 and 10. It can be equal to 1 but not equal to 10. So it's basically a single digit number, decimal point, and then everything else. And m has to be an integer. So very specific scientific notation. .7 times 10 to the 3, that would be scientific notation. .075 times 10 to the negative 8. Okay, so first thing is let's convert back and forth real quick. So this is in the exercise set number 8, 3,700,000. So the idea is I'm going to put the decimal place after the first number that's not a 0, to the right of the first number that's not a 0. So this is not a 0, so it's going to go here. 7, I can drop all the unnecessary zeros. And then since it's power 10 is a place value. So there's 1, 2, 3, 4, 5, 6. So it's times 10 to the 6. Now the way that I like to emphasize the remembering is this times 10 to a power is really what's moving the decimal place. So if I times this by 10, it moves the decimal place one place to the right. 100, 2 places. So when you're thinking, is this going to be a positive or negative number, I always think from the perspective of this number here, times 10 to the 6 is going to make 3.7 a bigger number, so that's going to move it to the right. Okay, so it doesn't matter which way I'm converting, I'm always thinking about the times 10 to the power. That's the thing that moves the decimal point, not me or you. That moves the decimal point. Yeah, about 14. Okay, there's 7 zeros. 6. Again, so I'm going to move the decimal point to the first place after, or I'm going to move it to the right of the first number that's not 0, so it goes here. And I'm going to count, remember this is moving the decimal point, so the perspective's from here. So if I want it here, and I want to move it to there, I'm going to have to move it 1, 2, 3, 4, 5, 6, 7, 8 places. I want this to get small, this number to get smaller, so that needs to be -8. That's the way I keep it straight personally. Okay, so Um, 10 to the 8 moves it 8 places. Negative is going to make it, this number is going to become smaller, so I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 places. So those are equal to each other. Okay, so let's convert the other direction. So convert to decimal. Or standard notation. 8.6 times 10 to the 8. Again, we're multiplying by 10 times 10 times 10, so that's going to get this number bigger, and it's going to move it 8 places. So that's 1, 2, 3, 4, 5, 6, 7, 8. Double check that. So it was there. So 1, 2, 3, 4, 5, 6, 7, 8 moves to there. Okay, so 3, 6, 7, 8. All right, that's right. So that's 860 million. Try 26. 4.27 times 10 to the negative 2. So the negative is going to make this number smaller, so it's going to move it to the left 2 places. So 1, 2. So that would be 0.0427. All right, so it's simple as that. Now, the way I can use this when I'm multiplying, so let's try number 36. 4.26 times 10 to the negative 6 times 8.2 times 10 to the negative 6. Oh, before we do this problem, I want to talk about significant digits. So the idea of significant digits and rounding is when 2 or more measurements written in scientific notation are multiplied or divided, the result should be rounded so that it has the same number of significant digits as the measurement with the fewest significant digits. Okay, so the reason is if we're doing something, basically when you round it, then your answer is not exact. So usually when you're dealing with large numbers, this has 3 significant digits. This one has 2. So when I get my final answer, I'm only going to be accurate to about 2 significant digits. So when I give my final answer, I'm going to give 2 significant digits. Now, if these weren't estimated using scientific notation and they were exact numbers, then of course you would use whatever the digits are. But here we're assuming that they've been rounded already. Okay, simplify, write scientific notation. With correct number of significant digits. Okay, so the way we do this is all multiplying, so I can switch these two and actually do these numbers. So I'll punch this in my calculator, and then I'll use exponent rules for this portion. So exponent rules, So let's do that first. That's 10 to the, you're going to add the exponents, negative 12. And this I'm just going to multiply using my calculator. So 4.26 times 8.2 is 34.932. And we want it in scientific notation, and we want to use the correct number of significant digits. So this has 3, this one has 2, so we're going to use 2 significant digits. Okay, so I'm going to round it to 2 places, so that's 35. And then of course this is not scientific notation, you need the decimal point there. And this is, if I times this by 10, that will make 3.535. So these 3.5 times 10 to the 1 is the same thing as 35. But we also have this 10 to the negative 12. So I combine that, and using exponent rules, 1 plus negative 12 is negative 11. So this is my final answer to 2 significant digits. Let's do one more. Well, let's do a dividing one. So how about 46? 4.0 times 10 to the negative 6. 8.0. And then for this one, same thing. I can kind of split it up, and I can just do the division here. And then use my exponent rules on the powers of 10. So 4 divided by 8 is 0.5. Negative 6 minus the minus 3. Okay. Now we only need 2 significant digits, so we're okay there. And then we're going to write this in scientific notation. Now for 5.0 to be 0.5, I need to move the decimal. This is where it's being moved. This has to get smaller, so this needs to be negative 1. And then combine my powers of 10. Negative 1 plus negative 3 is negative 4. So it's 5.0 times 10 to the negative 4. All right, let's do a couple of word problem ones, examples. So number 62 says a ton of $5 bills, so a ton would be 2,000 pounds, is worth $4,540,000. How many pounds okay, so how many pounds does just one $5 bill weigh? So let's see, so a ton is worth 5. So how many, so 2,000 pounds, so let's write it like this, equals 4540000 dollars. So we want to know how many pounds. We want to know how many pounds does a $5 bill weigh. So we want to know 1 pound. No, we want to make that X pounds for $5. Okay, so we can set up this proportion, and let's write this as so basically I'm just going to multiply by that. So I'm going to cross multiply both sides by 5. And you see the dollars cancel. And X will be equal to, so I'm going to do 5 times 2,000 3, 6. So that's going to get me 10. Okay, so I'm going to go 10 divided by 4.54. And that's 2.2 times 10 to the negative 3 pounds. There you go. So one $5 bill weighs 2.2 times 10 to the negative 3 pounds. All right, so that concludes lesson 1.7 and also concludes the lessons for chapter 1. So make sure you go to my math lab, do the finish up 1.7 homework and for the whole chapter, and then do the chapter tests under the menu tab for tests. It will be assigned tests. All right, so I will see you next